in spanning forest.
Or trees.
Trying to spanning trees. Okay.
Forrest. Thanks. Yeah, I'd like to thank the organizers for inviting me to talk here, and Greg for being around, and all the fun discussions we've had. In fact, the picture that my daughter drew, actually, 10 or 11 years ago, I guess, when I was visiting Cornell. Hasn't changed a whole lot. She's a lot older now. What? Oh, yeah, the microphone. How's that? No, not working? Is that better? Okay. Spanning trees are a very classical model of, not really statistical mechanics. One reason they're not as studied as much in statistical mechanics is because they don't, have any phase transitions in them. But I want to nonetheless show that for planar graphs, you can cook up some interesting transitions in there. And let me just start with the basics on the relation between the Laplacian and spanning trees, from the combinatorial point of view, right? So I start, G is a graph. Is there a pointer here? Yeah. I'm going to put a conductance on each edge, so it's a positive real number. And then the let's start with the finite graph. So associated to the conductances, there's the Laplacian operator, right, which is, well, everybody knows that, I hope. It's just the place the conductance comes in is you take, if you want to apply the Laplacian to a function at a vertex, you take the function, subtract off the value of the neighbor, and then multiply by the conductance, and then sum over all the neighbors. And the famous theorem of Kirchhoff, 150 years old now, is that you can actually count the number of the weighted sum of spanning trees of the graph using the determinant of this matrix associated to the Laplacian. Well, what you do is there's a natural matrix associated to the Laplacian operator indexed by the vertices, and you just remove any row and column from that matrix, and you get a new matrix. Let's call it delta sub 0. You can think of just making one of the vertices of the graph, designating that to be the root of the tree, and then you have the Dirichlet Laplacian for that. With that root, and then so that counts the number of spanning trees. Well, it's a weighted count of spanning trees. If you set all the conductances equal, of course, you get the number of spanning trees. Okay, so there are many different ways to generalize that theorem. Recently, Foreman gave kind of a nice sort of generalization which adds some geometry to the setting, right? So what we're going to define is a so-called vector bundle Laplacian. So it's no longer going to be a Laplacian on functions on the graph, but functions on sections of a certain bundle on the graph. So what does that mean? Again, we're going to start with a graph and a conductance, positive conductance on each edge. But now we take our favorite vector space W, right? And then over each vertex of the graph, we're going to put a copy of our vector space. Okay, let's call that W sub V over vertex V. And so now on each edge, we want to define an isomorphism between the vector spaces on adjacent edges. So we pick some, whatever isomorphism we care about. Let's call that phi VW. And when we go, so it's an oriented object. When we go backwards, we want to take the inverse of that isomorphism, so that if we go out and come back, we get back to the place we started. So that's called a connection, or the parallel transport on that edge. And well, because it really connects vectors from one vector space to the vectors to an adjacent vector space. And in this setting, there's also a natural Laplacian, which is defined in a similar way, right? So now a function here is a function taking values in the vector space. So f of v is a vector in the vector space w sitting over v. And well, so when I apply the Laplacian to a function, to a section now, I'm calling it f again, but it's easy to you know, think of these things as functions. But so what you do is you take f of v, and you want to subtract the value at the neighbor, but of course the value at the neighbor lives in a different vector space. So what you first is you take the neighboring vector and you drag it back to the vector space where you're sitting using the parallel transport. So I take f of w, which is the value at a neighbor, and then I use the isomorphism, which takes me from w to v, to drag that vector back, and then I can add it to the vector f, or subtract it in this case. Okay, so now f of v is a vector sitting over v. This thing is a vector sitting over v. I can subtract the two because they're in the same vector space, and multiply by the conductance, which is just a number. Right, and then I sum that up over all neighbors. That's the value of the Laplacian. Gives me a new element of that vector space at v. So it's an operation from a section to a section. But well, if you want to think about this, you can just take, if you want to think about it sort of globally, or in a more elementary manner, you can just take the direct sum of all these vector spaces, and then it's a linear operator on this big vector space, which is the direct sum of the vector spaces over each vertex. Now, the reason you might be interested in this, one reason why you might be interested in this is because well, in certain circumstances, you can choose a connection which somehow models some more interesting structure of your graph. For example, if your graph has some geometric structure like lives on a curved surface, or something of this type, you can find a connection which has some natural metric structure. And with Adrian Castle, I didn't talk. I'm not going to discuss that here, but we did analyze the what happens to this spanning tree model on a curved surface or a curved manifold. But anyway, the first theorem in this context was by Robin Foreman, and he discussed the case of a line bundle. So it's just a one-dimensional vector space over each vertex. And of course, when you have a one-dimensional vector space, the connection is just scalar multiplication. What's an isomorphism between one-dimensional vector spaces? It's just multiplication by a non-zero number, real number or complex number, depending on whether you're dealing with complex vector spaces or real vector spaces. And in this case, the determinant of the Laplacian now, this vector bundle, this line bundle Laplacian, has a combinatorial interpretation, which is also counting some tree-like objects. Here, maybe I should show the objects first, and then we'll discuss the formula. So now the objects are called cycle-rooted spanning forests, CRSF, and they look kind of like this. What is a cycle-rooted spanning forest? It's a subgraph that is a collection of edges of your graph, where each component has a unique cycle. So each component looks like a tree with one extra edge. I don't know if you can see the colors here, but there's supposed to be 4 different components, right? There's a blue one. This big blue component looks like a tree everywhere, except there's one little cycle there. So it's a forest where well, it's not really a forest because each component is a cycle-rooted tree. Feel free to stop me if there are any questions here. I've given this talk a few times before, and sometimes I will skip some of the definitions. All right, so let's see. What? Okay, so what's the statement? The statement is that the determinant is the sum over a cycle-rooted spanning forest, like on the following slide. Then you get each subgraph has a weight, which is the product of the conductances that it uses. But then it gets an extra weight, which depends on only on the cycles in that graph. And each cycle now has associated a monodrome W, which is the when you have a cycle in a graph which has a connection, you can start at some vector space, follow the parallel transport around the cycle, and when you get back to the place you started, you have a map from the vector space to itself. And because this is a line bundle, that map is just multiplication by some number. And that number doesn't depend on the choice of basis for any of the vector spaces along the way. So it's actually something well defined as a function of the cycle. That's called the, what's it called? The monodromy around the cycle. Okay, so associated to each cycle is a non-zero real number for a real vector space. Let's call it W, and then you take the product over all the cycles in that tree, in that forest rather, 2 minus W minus 1 over W.
When you say you have a product of the C's on the trees, it means you don't take the C's along the loops?
No, you take the C's on the cycles and the branches and the bushes. Everything. All the C's. Yeah, this is a product of all the C's in the, tree plus its cycles. But this, right, okay. Notice, of course, that if your connection is trivial, that is, if each isomorphism is just the identity isomorphism, then the monodromies are all going to be 1, and this will give you 0, which it should, because then you're just getting the standard Laplacian, which is a singular matrix because the constant functions are in the kernel. Okay, so okay.
Well, okay. The main example I think of the W as being e to the I theta or something. The W's tend to be
the W's
complex numbers.
That's a standard geometric context. If you're dealing with a curved surface, it's natural to use like a Levi-Civita connection or something in which the monodromy is somehow measuring the enclosed curvature, and then it would be appropriate to have the monodromy be, or the parallel transport be e to the I theta, so that when you go around the loop, the amount of monodromy is going to be e to the enclosed curvature, e to the I theta, where theta is the enclosed curvature. Yeah. But I don't think in this talk we'll need that.
So, what's the underlying graph on which your cycle root spanning firsts are?
So far, it's any graph.
Right.
But notice that there's a proviso in this theorem that we're only dealing with line bundles. Okay, there is a statement for rank 2 bundles. I mean, 2-dimensional vector spaces. But for larger vector spaces, even though we can define the Laplacian, we don't have any combinatorial interpretation of its determinant, except in rank 1 and rank 2. This is the rank 1 statement. That's the only one I'm going to use in this talk. All right. Was that your question? Yeah, but the graph can be arbitrary. Okay, but so what I want to study is just the very simplest example of this, which is going to be a line bundle here. And my graph is going to be a graph on an annulus, or in this case a cylinder, if you like, with a so-called flat connection. So what does flat mean? It means that, our graph is embedded on a nice surface, this cylinder, and what we're going to do is find a connection so that around any face there's no monodromy. Every face is trivial. You only pick up a monodromy when you have a topologically non-trivial cycle. So the way we can accomplish that is just make the parallel transport be the identity on every edge except along a single vertical path of horizontal edges, like this zipper, right? And on those edges, we're going to put monodromy Z. Z is think of Z as just being a non-zero complex number on this edge. So if we go this way, we get a Z, and if we go that way, we get a Z inverse. But all the other edges, the monodromy is trivial. The parallel transport is trivial. And so notice, if I have a cycle here which is topologically trivial, like this one, I'm going to pick up one Z and one Z inverse because I'm going backwards, and then the net is the identity. Okay, so now if you interpret the Laplacian determinant, let's go back to the statement here. In this case, the contribution for a cycle root spanning tree is going to be 0 if I've got trivial monodromy. So the only cycles that give a positive contribution to this sum are the ones which wind around the annulus. And since a cycle is, by its nature, has to be a simple curve, it's going to have to wind exactly once around the annulus. And if it does wind once around the annulus, the monodromy is exactly z, or z inverse, depending on which way it goes. So the net result is that this determinant here in this setting, each CRSF here is going to contribute 2 minus z minus 1 over z to the power k if it has k loops, k disjoint loops winding around the annulus. Right, so ck here, so I could just write this determinant as a sum over k of some coefficient times this quantity to the kth power, where that coefficient counts the number of cycle-rooted spinning force with exactly k non-trivial loops. And by non-trivial, I mean they wind exactly once around the annulus. Okay. Well, let's see. So now I've associated to this graph on an annulus a certain polynomial, well, a Laurent polynomial. P of z is now, well, there's only a finite number of terms here because in this case, I can't have more than 6 cycles. The cycles have to be disjoint, of course. So it's a Laurent polynomial in z, and it's some object which is actually canonically associated to that graph embedded on the annulus. If I take any flat connection, any other flat connection with monodromy z going once around, it'll be essentially equivalent to this one under some natural gauge equivalence, and it'll give the same answer. So right, so now what are the roots of this polynomial? Right, it's a polynomial that you canonically associate to a graph on a cylinder. Well, one way to think about these roots is as follows. If I unwrap this cylinder to a bi-infinite strip graph, and I take the universal cover of the annulus, right? Say the circumference is m here, so I can unwrap it and get this strip. Then, well, what if if I'm a root of p, then I'm a root of the determinant of the Laplacian, and that means this Laplacian matrix here is singular, and if it's singular, it should have a non-trivial kernel that is a harmonic function, right? Something which is in the kernel of the Laplacian is a harmonic function. Well, it's really a harmonic section, but when you unwrap it, you can think of that as a section on the graph as a function on the universal cover here, which has the property that when you translate by one fundamental domain over, you just multiply by z. So maybe that was too much to say all at once, but if I've got a function which is in the kernel of this matrix, then it has the property that locally it's just harmonic, because there's no I mean, the Laplacian really does look like the standard Laplacian at every point, except that when you go around once, the value of the function gets multiplied by z. So what I get on the strip is a harmonic function on the strip, which is, it's not periodic, but when you translate by one fundamental domain over, it gets multiplied by this non-zero complex number z. So the question of understanding the roots of p is the same as understanding these z periodic harmonic functions on an infinite strip graph. Does that make sense?
M is arbitrary.
M is the circumference of this thing. When I unwrap the thing, M is what I get by one fundamental domain. So you guys all know examples of this phenomenon from complex analysis, right? There are functions on a continuous annulus which are harmonic, and when you go once around, they multiply by z. Well, don't we? Let me think about that, and I will tell you what the answer is. You guys think about it too. All right. Well, we've kind of gotten off track here. What is the combinatorics interpretation of these things? Well, let's go back to our spanning trees. Right. Here's a sort of combinatorial interpretation of those roots. Right. Let's take a infinite strip graph, right, like the one from the previous slide. And if I take a spanning tree on that infinite graph. It has almost surely just one component, like in the upper picture. But nothing is preventing me from considering a different kind of measure, which is, let's call it mu k, this probability measure on configurations of, well, let's see what to call them. They're forests, so each component is a tree, a bi-infinite tree, right, and they're disjoint from each other. So I call these essential spanning forests with k crossings. So I have k components, each of which is a tree and is, you know, has two ends, one in each direction. Right, so the spanning tree is a special case, and mu1 is just the usual spanning tree. This is a part of a mu2 configuration. All right, and it's not so hard to show that if you want to just count configurations, like Kirchhoff did with the determinant of the Laplacian, there is a way to count them, and the growth rate of the number of configurations for mu k is the product of the first n minus k roots of this polynomial p. So turns out that p has only real roots. This is a non-trivial fact. And, well, by their nature, for every root lambda, there's a root 1 over lambda. That's because p has this sort of reciprocal form here, right? For every root z, the 1 over z is also a root. But if you look at just the roots which are bigger than 1, they're all distinct. And if there are exactly n minus 1 of them, where n is the maximum number of components you can fit in there.
Right now you have a fixed vertical height?
Yeah, I have a fixed graph, right? It's a strip graph. In this case, the width is 3. I can fit in 3 distinct bi-infinite crossings. Right? Mu k, k runs from 1 to 3 in this case, right? And so there's going to be, well, if I got this right, there's going to be 2 roots. I'm worried that I'm off by 1, but we'll see in a second. All right, I think. In any case, so the number of configurations is the product of the roots which are outside which are bigger than 1, but right. So if k equals 1, if you're looking for trees with 1 component, then that has the maximum growth rate. It's the product of all the roots which are bigger than 1. Right. So when k equals 1 here, I'm going to take the product of all the roots, lambda 1 through lambda n minus 1. That has the maximal growth rate. If I'm interested in components with 2 crossings, then I'm just going to take, lambda 1 times lambda 2. No, lambda 1, just lambda 1 in this case. Right, k equals 2, I go from lambda 1 to lambda n minus 2, which in this case is 1. So, and lambda 3, of course, has a growth rate 0, a growth rate 1, rather. Well, 0. So, okay, by growth rate, I should say this is the exponential of the growth rate. Anyway, there's some formula which tells you how these things grow, and related to the roots. And the more interestingly, this measure, just like in the spanning tree case, the uniform spanning tree case, each of these processes is determinantal for the edges. Right? The edges are, for each mu k, the edges are still forming a determinantal process, and in fact, the kernel is the same. Well, essentially the same, calculated exactly the same way for each k. That is, the determinantal process is a probability measure on, in this case, the edges, where the probability of some finite set of edges is defined by a determinant of a minor of this infinite matrix, capital K here. So if I have 2 edges, EI and EJ in my graph, and EJ is in the fundamental domain, which is shifted by x from EI, then this kernel has this formula in terms of some integral involving why is there there's no w in the denominator? That should be just a p of z, involving some Fourier coefficients of some rational function with p in the denominator. And the only place k enters into the formula is the contour of integration here. So you know, if you look at the set of roots, which so there's one of the roots is 1, and there's a couple roots out. There's some roots outside, and the reciprocals of the roots are inside the unit circle. You know, if I want to compute the standard uniform spanning tree kernel, I would just, you know, integrate over this circle. If I integrate over a slightly larger circle, which encloses also the first root, then I will get this, the kernel of the determinantal process with 2 crossings. And if I go out past another root, I'll get one with 3 crossings, and so on. So it's kind of an interesting story that this one function here, right, has several different Laurent expansions. Right, this is something you learn in complex analysis, right? If you have a function with several poles, these are of course the poles of the zeros of the denominator, therefore the poles of the function. In each annulus, there's a different Laurent expansion, and those different Laurent expansions actually give you the coefficients in the kernel of the determinantal process defining this edge process. So you know this slightly obscure thing you learn in complex analysis actually has some probabilistic use here. I'm happy with this because I taught complex analysis just, you know, very recently. Of course, I don't talk. Well, okay. So now let's. At some point, we have to come to these phase transitions. So we're right. So I discussed this already. Let's take a larger graph now, a wider strip. So here I took just a square grid graph. It doesn't have to be a square grid. You know, this works for any planar graph on a strip or on a cylinder, which you unwrap. But if the width is 32, that means I'm taking a cylinder of height 32, all right, and you know, well, so it's infinite left and right, but it has height 32. Then there are 64 roots to that polynomial. So you know, you can have anywhere from a tree with 1 component up to 32 components, right? And the roots have this very nice smooth curve here. It's not terribly interesting. Well, you can see that at 32 it crosses 1 here. 1 is one of the roots, and then everything up here is a reciprocal of everything over there. But let's make a small change, which is to use non-constant conductance now. And what I did is I put all the conductances 1 except on this row of sort of every other vertical edge has conductance 2. Right? This seems to be a mild change, but when you see some very different structure to this set of roots, it looks like this. All right, so there's a gap, and the gap occurs, I think, at 48, right, which is sort of halfway between 32 and 64. That's what I mean by density of half. So, right, when you pack in, you know, you can pack in at maximal 32 different crossings, but if you pack in exactly 16, then something interesting happens when you try to fit in the 17th one. So, you know, I have a little story about this, describing what's going on here, which is, you know, when you get on an elevator and you're by yourself, you can stand anywhere. But when somebody else gets on the next floor, you sort of naturally, your antisocial behavior takes over and you go to different corners. All right? And then a few more people get on, and people kind of want to spread out to, you know, stay away from their neighbors. Right, so that's what's going on here, right? Right. The first, you know, if I'm sort of looking at the uniform spanning tree, there's only one path which goes through this strip, and it's free to wander up and down as it likes. But then when you put in the second guy in, you know, it costs you. Well, so the first guy, its growth rate is a product of all the roots which are bigger than 1, which all these roots here. But the second guy, it costs this much. You know, it costs quite a bit of energy. You have to remove that last. Well, in this case, it costs a factor of 8 or so. But the next guy who comes in also costs something. Costs more, right? Not quite as much as 8. and so on. And right, so the elevator gets crowded after a while. All these different paths are trying to get through. But so imagine that your elevator is, has this tiled floor with black and white tiles. When your elevator gets to roughly half full, slightly less than half full, then everybody can stand on a black square, and everybody's roughly equally dissatisfied, right? But they have their own little area, right? And then the next few people who come in fill in the remaining black squares, and the people in the back of the elevator don't really care, right? That's the fact that this thing is sort of. I've got it backwards, don't I? I should be removing from the. Let me go on with the story, and we'll see if it matches the picture. So, the elevator is 50% minus epsilon full. The last few people can step on those black squares, and nobody really minds too much. But then, when all the black squares are full, the next guy wants to get on, and suddenly it causes trouble because he doesn't have any black square. He's suddenly got to push. He steps on the white square, but then those black people back up, and then suddenly there's this big effect, and that's this big gap, the drop in the relative growth rate, where it's actually harder to push in one more guy. Okay, do you buy it? Anyway, that is the some sort of rough understanding of what's going on. Anyway, okay, so let's go on. You can do the same thing if you put in some sort of. This is a sort of 3 periodic one, right? So I put in weights 1, 2, 3, 1, 2, 3, 1, 2, 3, and you can see that there are some two gaps there, which occur at density 1/3 and 2/3. Right? So something interesting is going on at those locations, right? Those measures, mu sub whatever they are here, 36 and 42 are something special is going on. Remember, these are measures on our strip, on our set of spanning trees. And so what happens is that at that precise value, these paths, which were originally sort of wandering randomly around, suddenly want to be localized. Suddenly, everybody falls into their own rut. Everybody's on their black square, and they remain very close there. And if you look at the sort of decay of correlations sort of vertically, that is how much one path is influenced by somebody else at the same time, at the same x location, they decay exponentially rather than polynomially at these intermediate locations. I put exponential in quotes because, after all, it's only a finite width thing. But now we can take a limit. Well, before I take a limit, maybe I should. Yes. So it is possible to make a limit of that picture and make perfect sense out of it, but somehow it's easier to discuss rather than discuss this case, the case of a graph on a torus, right, which is just the sort of slightly more general, slightly more complicated than the previous case. So now we have a torus, which is, in this case, I'm just going to take an n by n grid, and glue the left side to the right side and the top side to the bottom. And again, we want a flat connection, but this time means make the parallel transport be trivial everywhere except along the zipper of where I get transport z when I go to the left, and a horizontal zipper where I get transport w when I go up. So now I have again a Laplacian in this setting, which now depends on these two variables, z and w. And again, my cycle-rooted spanning forests are going to be trivial if they have cycles which are topologically trivial, contractible. But if you have a cycle which winds around the torus, this way it'll pick up a z for monodromy, that way it'll pick up a w for monodromy, but it can also wind in some other slope direction, and it'll pick up depending on the homology class of that cycle, it picks up z to the number of times it winds this way, and w the number of times it winds vertically. So the formula is a little bit more complicated. Looks like this. This is, again, just Foreman's theorem. This polynomial is, again, a sum over cycle-rooted spanning forest on the torus, right? Again, you get the product of the conductances. And now the interesting term is this one, you know, 2 minus the monodromy minus 1 over the monodromy. But now the monodromy is z to the I, w to the j, where ij is the homology class. All right, so so I did a very small example here. This is like a graph on a torus with just 2 vertices, right? So you should think of the top as being identified with the bottom and the right on the left. And here's your p. Just to be perfectly explicit here, what does your cycle rooted spanning forest look like? Well, it could be just consist of the two horizontal edges, in which case the monodromy is 2 minus z minus 1 over z. The monodromy is z, so that's the weight, and the factor of 2 is because I put a conductance 2 on that single horizontal edge. And then there's one configuration which has 2 vertical edges. That's the weight, and there's a total weight of 6, where I have one vertical loop, right? Well, if you think of this polynomial here, if you look at the exponents of w and z which occur, they form a just draw the exponents here in the z2. They form the convex hull is a polygon called the Newton polygon of the of P, and you can read the homology classes from this Newton polygon. Well, so right. Right. So this term, which had 2 vertical loops, contributes a w squared and a 1 over w squared, which is these 2 points. It also contributes something to the interior. This term is the one which contributes to these 2 points. So every time you have a cycle, you can think of it as going one way or the other way around. So it contributes symmetric points around the origin. The origin is in the middle here. Well, we can't talk about the roots of P now because it has 2 variables, right? But it does have a variety, a 0 variety in C2, which is going to be relevant for us. And I'll draw a picture in a second. But we can take a cover of our torus here, and there's a way to relate to compute the Laplacian on the cover, on the graph on the cover, to the Laplacian on the graph, on the original graph. And all that happens is the Newton polygon, which I drew on the previous slide, gets scaled up by a factor of, well, in this case 10 if I'm dealing with a 10 by 10 cover of that torus, right? And if I take larger and larger covers, all that happens is my Newton polygon gets filled in with many, many integer points. Each of these integer points corresponds essentially to a different homology class of a cycle-rooted spanning force on that torus. And so, in the sort of limit as n gets large, for each of these points in the Newton polygon, you get a class of here I'm skipping a lot of details. I'm sorry, but you get a class of cycle-rooted spanning force, where the number of components and their slope depends on the location of which point you're sitting at inside this diamond shape. So in the limit, you sort of get larger and larger torus. You sort of converge to the plane, and the measures you get one measure for each point in this diamond, which we should rescale the diamond so that it stays a constant size. And then an integer point in here will rescale to some real point s comma t, and so we get this doubly 2-parameter family of measures mu st of configurations of essential spanning force on the plane. All right, so these no longer look like UST measures because they have many components, and the components are all parallel to each other and have a slope which is related to s over t, essentially just t over s, and the density is also related to how big s and t are. I changed graph somewhere. This is a triangular graph configuration, but this is like, for example, a random sample from one of these measures. So you can see I'm just showing part of it, of course, but you should think of this as part of a configuration on the whole plane where my trees are now these long, thin objects which have a particular slope. In this case, going off in direction 0.3, 0.5, and a particular density. And so, for example, if you zoom into various special points in this diagram, you'll get very special configurations. Like if you zoom into the point over there, that's the point with the maximum horizontal flow, maximum horizontal number of components. So you get this one. Up here, you get that one. Right in the middle somewhere is the standard, uniform spanning tree, where you have essentially only one component. Okay, so it's a neat way to parameterize all these different measures, generalizing the original measure, which was the UST on the plane. And you can draw a picture of the growth rate here of μst as a function of st. This is all sort of standard calculations from the Laplacian determinant, and it's a what's this concave function of s and t. It's maximized at the very center, which is the uniform spanning tree measure. So as soon as you impose, well, if you sort of enforce having many components, then the growth rate, the entropy will go down, and it goes to 0 on the boundary. You can't really tell that here, but it does. Yes.
What's going to infinity here?
What?
What's going to infinity here?
Oh, I took a graph on a torus, and I took larger and larger covers, so it's converging to Z2.
Oh,
Okay.
So this way and this way?
Yes,
At the
both
same
both
rate?
both ways.
Okay.
Yes, at the
And
same rate. I took an n by n cover of the torus. Yeah, so these are measures on essential spanning force on the plane, on Z2, or on whatever periodic planar graph I had. So I don't know if you can tell from this picture, but there's some, oops, not supposed to see that yet. There's something interesting going on here and there. There's two points where this function, this entropy function, is non-analytic. Can you tell? You can kind of tell vaguely. Right? One here and one over there. And yeah, so this function, which is the growth rate or entropy of those measures of μst, actually is analytic everywhere except that those, in this case, except that those 2 points. Those 2 points are the ones which were integer points in my original Newton polygon. There's also an integer point here, but this actually turns out to be smooth there. And so, well, there's a lot to say here. But there's another way to draw this picture, which is the Legendre dual, and which just is, let's see, what do I want to say here? Anyway, rather than parameterized by s and t, which gave you the slope and density of these components, you can parameterize by x and y, which are the log of this variable z and the log of the variable w, absolute value. And when you parameterize, it's just an equivalent way to draw the same picture. Here, the picture fits the set of all phases is this Newton polygon n, and over here the set of all phases is it's the whole plane really, except that when you get outside these curvy regions, it doesn't matter what you do. This whole region outside here corresponds to that phase there, and the whole region up here corresponds to the phase there. So this diagram is a phase diagram in a different coordinate plane, the plane where you adjust the modulus of z and modulus of w. So for example, if we took z and w to be 1, like Greg had suggested earlier, e to the I theta, then we'd be sitting at the origin there, right? And then we would just get the uniform, that's the uniform spanning tree measure. And you can see in this parameterization, you can see these extra little regions, these ovals, which under the reparameterization, they map to that integer point there and there, right? Every region, the whole region inside this oval contracts onto a single point over there. And so those points these are points in these coordinates. It's kind of a funny thing, you know, as you move around inside that oval, the measure doesn't change. Kind of like what happens out in the exterior as well. As you move around out here, nothing changes in that measure. But over here they correspond to some sort of phase transition. But it's kind of it's the opposite kind of phase transition we're used to, because when you're off those points, the correlation decay for the edges is a polynomial. But when you're sitting at the measure at that point, the correlation is actually exponential decay. We call them, you know, in the Dimer model, we call them gaseous phases. But they're so I call them uncritical points. I don't know if that's a good terminology, but you know, they're points at which the model suddenly has exponential decay. Okay, it's kind of weird. But there they are, and they always occur at the integer points inside this Newton polygon. All right, and you know, you can deal with you can make very complicated examples by just taking a larger fundamental domain, or with some conductance function which is not periodic with period 1 or 2. Right, so these are examples with I don't know how many, 20 different phase transitions. Where do these measures occur? Some of you may know this model described by Gabe Carroll and Dave Spire, called groves or cube groves. So they invented this model coming purely from combinatorics and cluster algebras. And let me see if I can zoom in here. It's a model kind of like the Aztec diamond model, where you fit some random configurations together, and the only way they can fit together makes these shapes like this, and there's a nice Arctic circle theorem and so on. It's all a very beautiful combinatorial argument, but but the components actually form these trees, or well, forests really. And if you zoom in, you can see that each component is locally it looks like a tree, a bunch of trees lined up with each other, just like in the measures I was describing. And in fact, you know, one of my motivations for studying this whole model was to sort of understand this model here. So that's a place where these measures in UST, which I've been describing, occur sort of naturally in nature. Sorry, that was kind of redundant, wasn't it? Occur naturally, right? No. I encourage you to look this paper up if you haven't seen it. It's really quite interesting. Well, okay, so just to finish up, I wanted to show you some new simulations. We can also do the same with a massive Laplacian. So we take the Laplacian and add a positive constant m, called the mass. So now the determinant of this new operator, Laplacian plus m, in the standard case, counts rooted spanning forests with weight m per tree. So rather than counting trees, now we're counting forests, where each component has a chosen root, and you get weight m per component, right? And so we can ask the same question if we have a strip graph. Let's call mu k now the measure on forests which have, think of this as a bi-infinite strip graph, and we're looking for forests which have k crossings, which is a measure zero event for these for the standard Laplacian plus m, as long as m is positive. So in this case, there's a mu zero where you have no crossings, but then you can sort of condition on having an infinite crossing, or 2 infinite crossings, or 3 infinite crossings. And as you increase the mass, this it becomes less and less likely to have a crossing, and so all the other components get smaller and smaller. I have some much better simulations over here, which I just figured out how to do these really yesterday. So this is again part of a. I cheated. This is really a torus, but imagine that that's an infinite strip, right? And because I couldn't simulate an infinite thing, but I could simulate it on a torus. But right, so as you increase the mass, this is one crossing with mass 5, and so it's very unlikely. I mean, so all the other components are very small, but because we're conditioning on this thing being connected, it has this kind of interesting. It's no longer a loop race random walk. I don't know what it is. Maybe it's worth studying. I'm not sure. But right, as you increase the upper one is mass 1. You can kind of, if you look around, you can find the crossing there. It's slightly more visible in the lower example. So again, these are determinantal processes. The edge process is determinantal again. It's constructed in a very similar way. Simulating these things, took me a while to figure out how to simulate these things, and I had to, there's a small proviso here, which is I cheated. I mean, no, I didn't cheat. What I did was I used some simulation, and I don't know actually that I've converged to the actual stationary measure here. So that's something which hopefully we'll figure out soon. I think that's all. Well, okay. One more picture, which is that in this case, with the same weights as I had before, you can also make the graph the free energy as a function of the S and T variables, and unlike the previous case, it has a new non-analytic point, which is the point, the maximum entry point right there, and that is all. Thank you.
Thank you, Vic. Question?
In the groves, where do you see the uncritical points?
What?
In the picture of the groves, do you see the uncritical points?
No, that picture, they chose some parameters where there were no uncritical points, which you can do. Yeah, the reason we got the critical points is because I took these non-constant weights here, 2, 1, 2, 1, 2, 1. They took constant weights. But if you did that, you would see some facets appearing in their. Let me check. I have a picture, but I'm not going to be able to dredge it up right now. Yeah. See, in this case, yeah, it's sort of the density of edges sort of very smoothly throughout this figure. If there were some critical points, you would see some sort of floating facets in the middle there. But that's not the case here. Yes.
So how close is this situation from the dimer case to the height functions?
How different is it?
It looks very parallel to what you can do.
Yeah, it's very parallel. In fact, if you want to describe the limit shape,
match or?
it matches. Yeah. If you want to describe the limit shape behavior of these kind of objects, right? Here they prove that there's some Arctic circle theorem, which is actually a circle. There's some algebraic curve. All that goes through the same technology as we did with Andrei Okunkov for the dimer model, and in fact the same equation in the end. Somehow the fact that all these models are secretly free fermion models means that you get the same Berger's equation in the end once you figure out the right variables.
Can you see that at the combinatorial level?
No, that's also a sort of mystery, which is that at least in this case, I don't know any bijection with the dimer model, right? If somebody could tell me how to what is the bijection between the massive spanning tree model and the dimer model, that would be very interesting. And they have the same limit behavior. They're all described by very similar equations. Probably there's a bijection, but I don't know how to make it.
Other questions? Okay, just a reminder that we start at 9 o'clock tomorrow, and there should be a wine and cheese reception right outside the room here. And let's thank Rick again.